And I trust that everybody can now see our title slide. So welcome. Today, myself, Anna Clairborne, I am co-founder and SVP of Product and Engineering at Packet Fabric, and that's you, Kevin. And you're still on mute. I will introduce Kevin then. So myself and Kevin Landreth, who is our Director of Systems Reliability Engineering, will be presenting on metrics collection at scale and all the operational lessons that we learned the hard way. So in the beginning, how did our journey to large-scale metrics collection start? Packet Fabric was founded in 2015, and it was a completely greenfield network, which is fantastic because that is a very unique opportunity. It's not often that you get a chance to implement solutions on a completely blank slate. We knew from the beginning that we were going to have to collect a lot of metrics. We estimated our starter system would need to scale up about 200,000 operations per second. So this is not, in terms of both reads and writes. So it wasn't going to be a small first scaling effort. We also had the luxury of time for research because we were going to spend about 1.5 to 2 years in stealth mode. So we had luxury for actually researching different methods of doing anything as well as testing them out. And so how we explored this, or our methodology for exploring the problem space, was that we looked at the traditional wisdom for a solution, what the modern web scalers, hyperscalers were doing, and then also the future, what was out there in terms of alpha, what was hot, and what we could possibly grow into over the next year or two. So today in this presentation, we're going to explore the evolution of our metrics collection system over the past 5 years and the operational lessons that we have learned along the way. So for our basic requirements, we were going to be collecting network device metrics, DWM device metrics, and then server and a lot of other device metrics. For network device metrics, we're looking at physical and logical interface metrics, device level statistics like CPU, module temperatures, things of that nature, whether or not fans are okay. Also optic level information, both in terms of optical output and temperature of the optics, a bunch of different LSP level metrics, and some more stuff outside of that even. DWM device metrics, we're looking at a lot of the same things in terms of physical interface metrics, and then also chassis level, device level metrics for those. Servers and other devices like NPSs, console servers. We were looking at, network interface, bytes per second, packets per second, errors, CPU load, disk usage, and a whole lot more. We had, for the networking devices, our original suite of metrics just for the interface was 21. And then when you added on top all the chassis level metrics, we were looking at a lot more than that. Can't remember the exact number, but it was a lot more. We also knew that the system must be easily able to support multiple devices and vendors in every class, because we're looking at a wide range of DWM equipment, of Ethernet level equipment, and not to mention just every vendor under the sun for everything else, and a wide variety of server vendors too. So our initial target windows for collection, we wanted something that was fast, but maybe not unreasonably fast. We're looking for about 30 seconds to 1 minute intervals. It would be great if we could do 15 seconds or crank it down even more, but we decided 30 seconds to a minute was more than acceptable. And one of the things that we really wanted to do was keep data forever. If somehow that didn't prove possible, because storage has become super cheap and big data is very cool, right? We didn't know in the future what we could figure out if we were to store all these metrics forever, what we could do in terms of looking through them, patterns, trends we could discover over time, because I don't know how many networks out there that have all of their data saved since their inception. but this was a pretty unique opportunity.
Yeah, thanks for the intro, Anna. I had to get my microphone unmuted. So some of the things that we kind of wanted to get all in one interval was we wanted to get the descriptions, which most network operators are overly familiar with, but we also wanted to get some interface metadata, which was, maybe some stuff in a description or another other areas in the config. But we also wanted to like rapidly pull the OS version. And that seems kind of weird, but we'll get into why that is and a little later. But we also wanted to get some non-traditional stuff that gets pulled, which is like the optic, make, model, and serial. Um, so that some of that was because MTP breakout cables really break the whole. Oh yeah, this port. Because now you're taking a port and splitting it up into four ports over the fibers. It kind of breaks the original model of how to look at physical ports on a chassis and do some type of capacity management when it comes to that. But also firmware versions. Some vendors you can install the firmware on line cards, and you can reflash some of the optics as well. Uh, and as we made changes to some of these are all things that we were investigating at the time because we had a greenfield network. We wanted to be able to see when these happened. And the reason we wanted to pull them fast was because we needed the network team to operate autonomously. So how, from a systems perspective, how in the world are we supposed to know when something changes if they don't need to tell us? By pulling it really fast all the time, hopefully we can get some type of caching on the routers themselves. Probably not, but at the same time, we wanted to be able to just let the network do their stuff, and then we'll pick it up really quickly after the change is done, so our metrics line up directly with those changes. Um, Speaking of lining up data, one of the things we really wanted to focus on was making these types of events line up with our data. Um, for anyone who's ever done an RFO, these things underneath are going to sound really familiar. Because we do an upgrade, we have an outage, you got to go look at Rancid for the OS version and when it changed, when an optic swap out was via emails, and then look at your graphs to kind of see when this started happening and if these things line up. And having done that over multiple years, it was like a major pain point to try to figure out what happened with any network. And so we thought, well, if we have all the data very accurate, we can see exactly when these switchovers happen and get the data that's correlated, directly to these config changes because we saw the config change and the data change at the same time or roughly within the same window. Sorry about that. So, yeah.
And also the last point there is that the moving customers between ports and chassis without losing traffic data. Everyone at one time has experienced line card failures or even chassis failures where you have to migrate a massive amount of customers at a time. And if we weren't able to if those metrics weren't able to follow them, that would get very awkward for us, especially when we were claiming, that we were going to support retaining all these metrics forever. So our different approaches, which I covered briefly before, is that we broke everything into three broad categories. The traditional wisdom, which as soon as we look at it, you'll see it's all the things that have been done for years, the tried and true. The modern standard, so what the Facebooks, Yahoos, Netflixes, everyone was doing at the time. And then the next great things that were bleeding edge and alpha and beta. And we had four broad problem sets that we needed to conquer. And there's even a fifth one here that we're just kind of going to ignore for the sake of this presentation, which is how do we get the data from this broad array of devices, right? So we have data collection. Then we have data storage. So great, now we've got all of this data. Where are we going to store it? And then how do we retrieve it? We actually had two different branches for retrieval. We're only going to talk about one. We have customer metrics display, and then we have internal metrics display. Our internal metrics display is probably a lot more intense than the customer metrics display, just because we need to look at, you know, big, huge panels of data and be able to correlate them, whereas the customer data display is a more finite problem. You know, you're dealing with just 17 metrics per interface and 4 metrics per virtual circuit. So slightly smaller problem set there. And so for the display side, I'll just say quickly on the customer side, we were already very familiar with the d3.js library set, which allows you to do just about anything with data sets. And so we came up very quickly with our own little handy graphing system that displayed, you know, that could display data retrieved from wherever, and it looked nice, and we were pretty happy with that to start with. So we're mostly solving for the how do we do this complex and, you know, the more complex internal data display. So for the traditional wisdom, everyone here is familiar with SNMP, and I'm sure everyone wishes that it was dead already and still somehow lingering about today. But in 2015, this was definitely a standing default for device metrics collection. And it's still heavily in use. It was brought up, you know, by multiple people at the start of this. Well, we always have SNMP, and my thought was, I'm never using SNMP again. There's also device polling through NetConf. This is also a standard. You know, NetConf had been around for 10 years at this point. Pulling data via RPC calls was pretty standard. There's a lot of vendor-specific API implementations at this point in time. This was the point that a lot of vendors woke up and started to say, oh, my devices become more interesting if people can interact with them. So instead of necessarily picking a standard like NetConf or you know, gRPC or something like that, there was these one-off implementations, which are always sort of a pain to deal with. Because they're not following the standard. And Kevin, I like cron. I have no problems with cron. I have cron jobs that are still running today. Kevin is the one that truly hates cron, so I'm gonna let him elaborate on this point.
So yeah, so my biggest problem with cron has always been that it's too simple. Um, since I'm on the SRE side of the house, the one responsible for the polling and things of that nature, one of the things that always happened was the pollers getting died because they'd stack up on each other because of poor locking and other things. We'd also run into systems being crashed because, you know, again, either poor locking or the program crashing and then us getting like 1,000 emails, but then of course distributed to everybody on the mailing list. There's just a plethora of problems that come with cron just because it's so simple. There's no safety precautions over, you know, what happens. You know, what happens if your polling interval goes beyond the cron timer. Well, if you don't have everything set up perfectly, it'll start the second one while the first one's still running. And then now your metrics look even funnier. So I hate cron. That's big for polling stuff. Maybe it's fine for other things, but I still hate it.
Also, in terms of data storage at the time, Informix, I had worked a lot with Informix before big data was a thing. Back in the days of Tower Records, we actually started storing song clips to the tune of millions, you know, going from like 3 million to 10 million back in 2000. Informix was really good at handling a lot of data, so I naturally went and looked at the Informix time series. It is, of course, expensive because it is a commercial solution, and at the time it was very good. It was very fast, scalable, stable. It was all supported. And maybe it was sort of lucky that we never went that direction. I don't think we could have afforded it anyway on a startup budget, but in 2017, support for that product was transferred out of IBM. And I don't know where it stands today, but at the time it was definitely a nice standard. As far as display, there's RRD tool. Um, everybody has used it at some point in time. Everybody hates reverse Polish notation. I'm just rather noting that we did at least give a nod to that it existed and we weren't going to use it. There's a lot of other open source tools like LibreNMS, Zabbix, MRTG, of course, was still around. So we definitely gave all those a second look. Need to be fast with your mute button, Kevin.
I, I don't have any control over this. So, so while we were looking at things, SNMP was still really popular, even in the new and improved kind of polling solutions that were out there, which was a little disappointing to me because at this point I was tired of SNMP and importing, 7,000 MIBs, just to get a couple extra data points. Um, but they did start to do some interesting things, at least, which was at least not having all the pollers running in one cron job on a single host. They actually, worked really hard to figure out how to geo distribute the actual pollers and the timers, and so things actually scaled quite a bit with that regard and how the actual, you know, the data was collected. But one of the biggest drawbacks to how they were kind of addressing that is that they didn't change some of the fundamentals. So they were still writing to the database directly. So there was no type of buffering. There was no, like, what if your management network is disconnected? The device is still online. It still has statistics, but you lose all of them when it gets disconnected. Some of the other new storage systems kind of address this by allowing for network partitioning to happen. Cassandra and Elasticsearch worked really well in this regard. But some of them still just use RD tool or MRTG to store the data. So like there wasn't like any real improvement. Um, Graphite and Carbon were pretty mature by this point and were a really interesting prospect for us. And then of course you have the de facto large, data set monster of HBase, which seemed like for what we wanted to do and how we wanted to store the data, that seemed like kind of the way to go, but there was no correlation between the polars that were available and HBase. So like LibreNMS just uses RRD tool. Zabbix, I forget exactly what it uses, but then some people are still using MRTG just in they just spread it up by like regions. So you had to go to 4 or 5 different servers. Um, so it was better, but not substantially better, and definitely not in the scope of what we needed to address. Next slide.
Oops.
Okay. Is that one me? Okay, yeah.
Yeah.
So when we looked at it, it was super duper quick, right? Like this is Anna's OID. She probably remembers OIDs better than I do.
Yeah. It's if out octets. Yeah.
Yeah. But as everyone knows, even with just IP addresses in general, it's super easy to transpose stuff when you're debugging things. And then you're wondering why the counter is always zero, always zero. Oh, it's 22121. Oh, damn it, And so things like that really like slowed down your ad hoc troubleshooting without even more tooling. Even when we got vendor MIBs, like when we import them, not all of them would be complete, or maybe the MIBs were outdated from the actual platform that we were using because we were trying out a new platform from them. So even though we got MIBs from them, we weren't like getting the full data set. Like we could get the statistics, and we contact support and they give us the OIDs, but the pain point still existed for us. Um, and the other thing that really stinks about SNMP is that it's all UDP based. And so you have like these finite timers and you can see, like Did the packet get there or did the packet not get sent back? And it's really hard to diagnose that over UDP, of course. And if you have a hiccup in your management network, you have a hiccup on the device, is the device responding too slow at the time? These things, again, like we don't know when the device actually died, and we kind of have to correlate it with ping or some other, tool set. So anyway, we kind of decided that we were done with SNMP, didn't want to pursue it any longer, and yeah, we were just pretty much done with it at this point.
I need to learn my mute button as well. This brings us to the next great things. The big thing at the time was all streaming telemetry all the time. That was the big thing on the scene. So gRPC was the standard that people were starting to converge on. That was two flavors over TCP, over UDP. Some vendors, in fact, I will say most vendors had a partial implementation. Like you could get streaming telemetry on physical interfaces, but you couldn't get it for LSP metrics, for example. And then on a lot of devices that weren't routing devices, streaming telemetry still wasn't a thing. It hadn't even been heard of yet. The people that were still struggling for an API of any sorts. But anyone who was in the networking space at least had this in on their roadmap, along with some big claims that stream telemetry was going to provide data every second or even at sub-second, millisecond type intervals. The data storage in FluxDB was what all the cool kids were using because it was incredibly easy to roll out. I think one of the first time series data tutorials I ever looked at was in FluxDB. Cloud-based NoSQL was just becoming a thing. So NoSQL databases that you could actually deploy in the cloud. This was really interesting because of the ease of management surrounding them. HBase, Cassandra, none of those large NoSQL databases are easy to manage. The sharded SQL implementations of time series databases that weren't totally self-serve, roll your own, like Timescale DB, were in their very infancy, and they were like stealth startups at the time, which was even a little too alpha for us because it's something that definitely wouldn't be ready in time. Prometheus was an interesting project that came out of SoundCloud. We poked around at it for a while. It became open source, or at least that's the time that it started catching our attention, was right in 2015. It appeared very mature and robust. I think it had been in use for quite a few years at that time, and it contained monitoring and alerting, which was a great addition. The thing that really scared me about it is that it had its own query language, PromQL. I'm not a fan of learning these random, very obscure query languages, mostly because new things scare me. And also data display, Grafana. It was Grafana everywhere. That was the latest, greatest open source graphing tool in existence. And it was pretty cool. As far as the polling evaluation, a lot of us had a ton of experience with NetConf. We knew how it functioned. We were very comfortable with it. We had written with it, a multitude of data collection or update tools with it. It has RPC commands for just about everything. It's fairly consistent across vendors. We all know which vendors have the best implementations, but at least every vendor has some implementation that is relatively close to the standard. So that is the great thing about it. We also looked at RESTconf because this is around the same time that a lot of vendors started to have an implementation of RESTconf, which is just a less robust version of NetConf. And everyone was implementing it because we want it to behave like HTTP REST, which is great in theory. Because from a software engineering standpoint, REST is fantastic to work with. It is easier than RPC commands and the heavy overhead of XML and having to parse XML. I don't think anybody likes XML. I mean, there's times that its verboseness its verbosity and specificity are really great, but generally it's just annoying. Even from the RFC, RESTconf is not intended to be a replacement of NetConf. I remember at the time I read this and it always really stuck out to me because it's like, well, this is just sort of, this is a side, this is a sideline. Um, and again, most vendor implementations of RESTconf, like streaming telemetry, were missing support for some subset of data, and it just wasn't going to do. So it was netconf. We knew we were going to use netconf polling. There was pretty much no question about it at this point.
So when I was told that we were using netconf, because that was already decided before I came on, uh, I had kind of had to figure it out kind of figure it out and learn from them. And it turned out that you don't need a huge chunk of libraries to make it happen. There are some nuances between the different vendors, but it's some of the standardized commands, it's just as easy as echoing strings into the SSH client itself and invoking the netconf subsystem, which was really surprising to me about how easy that was to implement. Um, Anna's not a fan of XML, and I know most of the world isn't, so I'm kind of an outlier here, but I love XML when it's done right. Um, and the only reason I love it is because XPath. Um, For those who don't know, XPath allows you is kind of like a query string slash filtering language, so you can pull out stuff from XML, like with ancestors and children and all these other type of quantifiers, so you can see the exact data that you want in like a 4 megabytes of XML, and you can get like a few kilobytes of information that you want really fast. That is one of the things that came out of the 2000s. That's really nice is that someone spent a lot of time optimizing XML and XPath. So, which works great because netconf is all XML. Even when you use Yang and non-Yang, it all comes across as XML. I think there are some support for doing gRPC, but I don't think that's really a standard. I believe netconf is supposed to be all XML. But um, so for most of the vendors, we found out that, oh yeah, we can ask pretty much the same questions, or sometimes ask two questions to the routing device, and they're able to actually get pretty uniform data between models, which was really important to us because that was one of the things we were fighting with SNMP. And so when we were like, okay, hey, we want to see all the LSPs. Oh, okay, here, or ingress LSP, sorry. We could ask pretty much the same question to two different vendors, different questions, but roughly get the same data back, which is great because when you have a lot of ingress LSPs, there's a lot of data that comes back. So, but we didn't have to query like 6,000 OIDs over SNMP. We asked it one question and it gave us all the data back really quickly. Like we're talking like 300 milliseconds to get all the ingress LSPs back, which is a huge XML payload, by the way. But it happened really fast, and we didn't have to do all these round trips over and over and over to the device, which I'm pretty sure is expensive, not only from a latency perspective of collecting the data, but maybe on the devices as well. We all know they don't have like the best processors in the world, so I don't know why they keep getting cheaped out on. It's really frustrating. Anyway, so with TCP, we were able to find out really quickly when the device wasn't responding, because TCP is a lot more verbose when things aren't working. So and that was kind of nice for us from a correlation standpoint. We knew exactly when the polar broke and why. And it's like, oh yeah, the device isn't responding anymore. Things like that. Um, but because we only had to make like I think at the time 5 different calls when we first got started, we could get the whole config, all the network statistics that we wanted, and LSP statistics, and all the metadata that we wanted in a pretty quick 15-second window. We increased it to 30 seconds and sometimes 60 seconds depending on the processors in the devices. But otherwise, like we got everything we needed in just a few questions to the device. And what this did for us is it really simplified how much polling we had to do. You know, it was really exciting when I finally caught on to all this. Granted, I didn't implement all this myself. It was just me playing catch up. But so we had all this data, and it was really great, and we were super excited. But then it was like, oh yeah, where do you put all this data now? So next slide. Okay.
So yes, at the time, all HBase all the time. That was the current trend. Everyone was completely over the failed relational DB approaches to time series storage because they just fell over. I know that I tried storing time series data in MySQL before. It's incredibly difficult to manage those sharding schemes yourself. And HBase was incredibly scalable and robust. It was also incredibly difficult. There were, of course, a variety of roll your own solutions out there where people had invented their own thing. That wasn't so much for us. OpenTSDB, even though OpenTSDB was just a mechanism for data storage, it was a large project used by Yahoo and maintained by a few of the people there. And it had some extremely impressive performance statistics in terms of what it could do on existing large networks. It was in use in quite a few different places, and it had different backend storage options. So it could use either HBase, Cassandra, or Bigtable, Bigtable was actually like pre-alpha at the time. And so it was just a thought that it would work, and Google had created a client for it to do that. Between HBase and Cassandra, Cassandra is a nice masterless architecture, so it's a lot more fault tolerance. However, this leads to like data consistency problems. HBase is a mastered data storage. It doesn't have the same consistency problems. Also, just in terms of, HBase is more heavyweight. It relied on HDFS for underlying storage, and also Zookeeper, Apache Zookeeper for metadata management and status management. So there were big pluses and minuses to both of these. There was also InfluxDB, which was super hot at the time, but the performance numbers just simply didn't stack up when you were looking at the performance of Cassandra or HBase. So we just decided pretty quickly to slash that one off the list and not explore it any further because it couldn't get anywhere close to our base use case of where we needed this thing to scale to. OpenTSDB, just even in the exploration phase, they had a IRC channel on Freenode. The maintainers were very helpful and friendly. So even just in our exploration of that, we got comfortable with the idea that there was a good community around it and people to ask questions to, which was important for an open source project. And actually, I'll take the first point here because I'm the one that did the majority of the HBase testing and implementations. And it turns out that HBase is actually really, really hard to run. If you're doing a standalone implementation of HBase, it works pretty flawlessly. Once you work through the initial configuration problems and getting familiar with the Java ecosystem and the Apache tools, you can do it. Running an HBase cluster is not easy. It requires a lot more wisdom than I had. There's a lot of factors to both scaling OpenTSDB, how it is writing data across regions, as well as just setting up an HBase cluster to write data properly across those regions. And even in our, even when we were writing, about 100,000 test metrics a second and looking at this thing in a very closed, highly managed environment where we didn't have a lot of data in it, I kept ending up with hotspots, that is regions that would just get a ton of data written. And then can really fit, and then in the process of trying to figure out how to redistribute those writes better across the cluster, I pretty much uniformly always burn the entire HBase cluster down. And I verified things in the OpenTSDB documentation, such as that you can add a thing with OpenTSDB called a salt to increase how the data gets written across regions. And if you have to decide that at implementation time, and if you change it, later on, they warn you that all of your data will be corrupted. I verified that is in fact true. The documentation was accurate on that point. So the upside is that we got really good at installing and configuring HBase and Zookeeper, but could not avoid the common pitfalls of running these large HBase clusters, because we just didn't have the expertise. So it ended up not the winner. And Kevin, I'll let you take over for the rest of this now.
I can attest that Anna was very frustrated with how many times she actually burned down the clusters. There's many curse words. So TSDB still seemed appealing, even with all these caveats, it still seemed appealing because of how much large amounts of data it could store and query. And again, remember, this is for us, that we're trying to do a ton more data and data collection and storage than most network operators kind of do today. So we were kind of trying to go above and beyond and kind of push the limits of what you could do with network polling. And so, but even with all this, OpenTSDB and HBase still look like a really good fit for what we were trying to do. Like, had built-in Grafana had built-in support for it, so it was just ready to go. Even when you weren't using Grafana, like the query language for it isn't some obscure query language. It is a very tiny, in comparison to other things, JSON payload for when you want a really complex aggregate result set and everything else. And you get a very nice set of JSON arrays back. So implementing and retrieving was, a really, really easy way for us to get into OpenTSDB, and that was kind of like the big appeal. There wasn't like this huge technical barrier from the implementation side of things. But OpenTSDB and all this greatness, we start running into, oh, okay, we can store some data in it. And then, we ask on IRC, and the first response is always, yeah, you shouldn't do that. And almost everything we tried, it always felt like, oh yeah, you shouldn't do that. And so we started reading more and more and more. A lot of the experts helped us quite a bit for free, so thank you. But there's there's a salt width, which is, for people unfamiliar, salting is like basically pre-padding a string, so that way when you're hashing it, it kind of determines where it would potentially go in a table. You have to decide that before you ever write any data. The UID, which is the metric name, you have to decide how big those can be. You have to decide how many tags to allow on an actual metric, and that determines how many rows are written to HBase. So the more tags, the harder it is to read, because there's too much volatility. And so you have to kind of like already have a really good understanding of the data that you want to write, how you want to write it, and how you want to read it. And if you think of a new way to read the data, like how you want to look at the data, you can't go back necessarily and look at all the old data and provide a different viewpoint on it. You have to start writing the metrics in a new way. But you only get the data from that point on in your new kind of like dashboard that you kind of wanted. So really what ended up happening was that the schema ended up being really difficult to deal with. And it was like, oh, okay, we want to do these things. Okay, we did those. Oh, hey, it'd be really cool. And then we found out that's like, oh yeah, how do we take the old data and put it into these new metrics? And so every time you had to do that, the amount of value or the amount of storage that it took up was growing rather rapidly, even with compaction. Um, then also we also found out that HBase, or sorry, OpenTSDB actually stores all these values as floats, and float math is its own problem by itself, which can lead to some very odd numbers.
So taking, back to the storage is that we eventually worked through a lot of these issues with OpenTSDB. We ended up writing some key because of because of cardinality, and we ended up breaking up some keys and adding more data to them to make them less closely related and more easy to search for, and reinserting data. And we had to duplicate some data, and we had to do some things we didn't like, but we eventually did get a really good key schema figured out. But we still had this problem with HBase that we couldn't get past, is that HBase truly does require experts in HBase and the Java ecosystem to run. And so we looked at Bigtable. The integration with OpenTSDB was extremely alpha, but we liked what Bigtable had to offer. Bigtable is the original spec from Google that HBase was based off of. So it is actually the original. And having it be a cloud-based thing with a point and click interface and some pretty graphs meant that it was a big reduction in the problem sphere and overhead that we were dealing with. Bad news was, of course, that the existing version of OpenTSDB didn't work with async HBase. The shim that went in to actually sit in between OpenTSDB and Bigtable. And so a few things needed to be fixed. And this came down to me, since I had done all the HBase work and had at least now some familiarity with Java. And it's actually really, it actually always is a great irony to me that I'm the one that ended up doing this, because in college, the programming languages class, which is where you touch on sort of everything, where you touch on Lisp and Fortran and all these, more obscure languages, Java was the one I truly hated. And now sort of the fate of this entire system moving forward rested on me becoming an expert in a variety of Java things. And so I had to really dive into the Java, so the Jetty ALPN, which is the application layer protocol negotiation library. There was a lot of versioning conflict problems. So I got those worked out. There was other ALPN compatibility issues. And so made a few contributions to the project, learned a lot about that, and actually got it working. There was some other issue in the client itself that I can't remember now. But suffice to say that it was, it's not easy to take something that is pre-alpha, that is a release that was done by a vendor, to say, hey, you should use this and actually get it working and functional in a sustainable way with an open source project. But got it done. The initial stress tests of OpenTSDB in combination with Bigtable demonstrated super promising performance on a single node. I think it was like 10,000 writes a second. Of course, this didn't change anything with OpenTSDB in respect to its key design. And we could almost do an entire presentation on OpenTSDB key design, which is why I'm trying to keep it high level. So, Kevin, back to you.
So when we were trying to collect the data off the routers and switches, we were trying to figure out, well, how do we make sure that the data always is to TSDB, and we decided to use RabbitMQ for that. But what ended up happening is, if we had one TSDB node which can handle a plethora of writes on its own, what ended up happening is that even though we could store the data into Bigtable really quickly, like at 10,000 operations a second, which is kind of on par with what we were looking for, we had to add a lot of Bigtable nodes in order to get up to the standards that we want. At the time, since it was alpha or beta at this point, this was still a good solution for what we were trying to do. But unfortunately, because we're doing our own cool netconf parsers, we had to write our own OpenTSDB writers as well. So there wasn't any type of like ingest for the metrics, which are kind of handled by all those modern day solutions, so to speak. So by wanting to stay away from SNMP, we ended up creating more and more problems for ourselves. And one of those is scaling out the ingestion of the metrics into TSDB metrics, um, which is kind of where we run into this next slide. So one of the things that happened, oh, this is Anna's slide. Never mind. Sorry.
You can keep going with that.
Okay.
um, I, the great thing about the original design system is that it lasted us for 3 years. It got us out of beta and it got us quite a bit of revenue, so that's great. And we even at peak hit way more than we estimated as far as operations per second on this design. We had to make more than a few adjustments along the way. Our initial testing was really focused on write speeds, and we're like, reading data is easy, that should be no problem. We were really, really wrong about that because OpenTSDBs are in a connection pool with shared readers and writers, and we had to segregate out readers and writers because the reads were so much more intensive. So what we discovered is that the async HBase client used by OpenTSDB for Bigtable actually performed regular expression match against every single row in the database when it was reading data. It was not performing like native OpenTSDB and HBase, where it actually only scanned a specific subset of rows. It was scanning everything, so our reads kept getting incremental slower and slower, and we kept having to add more and more resources to do those reads. And this ultimately resulted in 100% CPU usage on a lot of our SSD Bigtable nodes. And this became really problematic because even though we could write all the data in the world, the value comes from displaying it both to ourselves and to our customers. And it was coming to the point where we could no longer do that. And Kevin, actually, I'll jump back if there's something you want to add there. Kevin was far more operationally into this than I was at this point, so I'm sure he has some horrible details that he can share too.
Yeah, so writing the data was really easy, as she said, and so we only had like a couple write nodes. But what would end up happening as well, because we had like a constant read level that we had to maintain with both the internal and external graphs. What ended up happening is if we did get disconnected from our management network, either due to our connection to Google flapping, or our transport provider having issues, any reason that we would lose our connectivity back to OpenTSDB, including OpenTSDB and HBase breaking on its own, we'd end up with this huge queue of metrics to store into OpenTSDB. But when you stampede OpenTSDB against an already loaded Bigtable SSD Bigtable nodes, which I think we were up to 12 at this point, the whole thing would collapse. So the writers would end up essentially locking up and timing out. And so in order to continue the metrics, you'd have to kill off the write-only nodes, wait for a little bit until the load went back down, and then start them back up. So we'd have millions of messages in RabbitMQ, like just trying to write to OpenTSDB. And this was like one of our largest pain points because even though we wouldn't lose a large chunk of the data, sometimes in order to get certain things back online, we would have to operationally choose. It's like, yeah, it's only been down an hour. Let's just nuke the data, and there'll be a gap in the graphs. And that was like one of that was kind of like the big aha moment. Is at least from Anna is what she put in her message to me anyway. Is that we need to stop losing metrics, because our whole system was designed to not lose metrics, and because of all the pain points we have, uh, adding more TSDB nodes wasn't cost effective at this point. Or yeah, Bigtable nodes wasn't cost effective at this point.
So one of the funner, more specific bits that we'll get into here is or one of the more fun specific lessons that we learned was about traffic counters. So traffic counters on hardware are monotonic, meaning that they increase linearly, other than that they occasionally reset to 0 for 32-bit counters, and for 64, when the device is rebooted. This is a fact that we all know, except for fun fact, this is not a fact. Many hardware devices like to occasionally go backwards with counters or return garbage, not a number values. And if you make the assumption that when a counter is less than the previous value, a reset has happened, and you do that calculation as though the number has reset, you will end up with some wildly inaccurate roll-up numbers for making this assumption. And this isn't a big deal if you're just graphing, but if you're doing something that is a bit more intricate, like actually billing based upon these numbers, that makes an incredibly big deal. So that was bad. And I think Kevin actually already covered at this point. So we'll go ahead and break over that one. One of the other things that we discovered is actually, Kevin, why don't you just take the rest of these, because this was where we're going to break anyway, even though you did that on the last slide. So go for it.
Okay, cool. So we're writing a plethora of data at this point, but because one of the reasons we observe metrics going backwards directly from the devices and actually not a bug from our software was because we're actually pulling these devices much faster than intended. At the time, 5-minute pulling was still kind of like the de facto standard, with 1-minute pulling being, oh man, make sure you know what you're doing before you get down to 1 minute. And we're doing anywhere between 15, 30, and 60 seconds, which is a minute, I know. Anyway, so we're collecting all these metrics at this really fast rate for every device, every time. And that's like 40 times more metrics than any traditional polling. And when you're trying to do something stupid like the data forever, get slower, slower. And also, if you want it for OpenTSDB, in particular, one of the things that you have to do is when you query the data set returned from HBase or Bigtable has to fit in the OpenTSDB node's memory structure. Or, yeah. Well, all this, you know what I'm trying to say. There's a lot, you have to fit it all in RAM. So you got to run like these huge, like 100+ gig OpenTSDB reader nodes just to be able to query more than a 24-hour period. But even with these large memory nodes, we couldn't actually retrieve the data fast enough from Bigtable. So it's, the next real thing is like, well, how do you do rollups and other things like that? We ended up having more and more problems with trying to implement those as well. Some of the OpenTSDB metric name problems, they have a very limited character set you can put in there that aren't necessarily compatible with some network components. And when you're trying to make that work and do character replacement, sometimes that can end up leading to naming collisions. And so what you end up with is this really weird thing called what we called floppy metrics, was where you would see metrics overriding each other in these fast intervals. So you would have like 6,000, 3 million, 7,000, 3 million, 1,000. So these metrics are going positive, negative, and it took a while to figure out that those cases were actually name collisions on the metric keys. A big disadvantage for what we wanted to do was store the raw data as well, which means you're not storing the rates of data. So when you want to calculate how many megabits per second this thing is doing, we're not storing megabits per second, we're storing the bytes. The way OpenTSDB handles queries, if you want to aggregate certain amounts of data, which makes it queryable, then you can't do rate conversions until after that, which causes a massive amount of downsampling. And so therefore your data doesn't look right. So instead of like a 10 gigabit, kind of line, you would be seeing like a 4 megabit. You're like, what? Then we know that they're doing a lot more. And it has to do with the way that OpenTSDB handles its order of operations, which you can't change the order of. Next slide.
So guys, I hate to do this to you, but I'm going to have to give a 5-minute warning. We've run over a bit on this presentation, and we're going to have to, get going with the agenda. So 5-minute warning. Sorry.
Nope, no worries. This is longer. This is longer than we thought it was going to be, I think. All right, Kevin, you can take this one and power through. Or I can take it. All right, so just quickly going through some of the other lessons learned is that since we're using Bigtable as a service, some of the costs grew a lot faster than we expected, which was, an unpleasant surprise. Backups of the data weren't possible because it was just too expensive or too slow. The pre-built releases of OpenTSDB were outdated and didn't include Bigtable support. So we had to constantly keep updating, various things within the async Bigtable client in order to get that to work. Removing any bad data was incredibly difficult and labor intensive, especially if two data sets were intertwined at all. You cannot store too many data sets within a single metric. And this was a horrible performance issue that was related to the regex thing that I mentioned earlier. And you cannot simply, one of the other hard lessons was that you can't simply store bytes in OpenTSDB and multiply by 8 to get bits out natively, which resulted in a lot of hacks to get bits to display. So the next thing was that we decided we're going to have no more dependency on open source systems. Our team is really great at writing and maintaining software. We're less good at waiting for the next open source release, and we're even less good at continually contributing to Java projects. Also, as it turns out, writing data is easy. This time we have to make sure we can both read and write the data. And the solution doesn't necessarily have to be NoSQL. We just thought it was really cool at the time, and it was the way to go. For big data storage, but there had been a lot of advancements in the meantime that meant we could use conventional SQL, which we had much better knowledge base in.
Yeah, so we still ended up doing polling, but we switched up a lot of the way we were doing polling. So we took our big kind of monolithic application where we were doing it all on the edge because we ran out of servers at the time and kept spending our money on routers because that's where our money was actually coming in from too. So one of the things we needed to do is reduce our edge capacity, or sorry, our edge load that we had because we just didn't have the capex at the time to buy more servers. So what we did is we split it up into 5 different applications, one just to handle polling, one just to handle like making sure all the polling data is like one cohesive vision, and then 2 different data set writers. Because this also allowed us to push like smaller changes, such as like adding new RPC calls to the routers without having to worry about processing them until later. None of this would have been possible without Kubernetes because we run 5 applications per device, and then 2 of those applications are state machines, which allows us to write the data in a much more effective way. We're heavily using RabbitMQ now, and one of the things that allows us to do is actually like monitor the messages in between each one of the services so we can still see what's going on. Next slide. And we had to figure out where to store it. Timescale DB actually ended up working out best here because they kind of fixed the whole time series in a relational database problem. We got to design the schema in a way that would work directly for how we wanted to ask it any type of question. Rollups are still a pain, so it's not a fixed problem, but it definitely is a lot easier than it used to be. We now don't have to do batch processing in order to get rollups; they're continuous. Counter rates work. But it's also a lot easier to find and have SQL gurus instead of OpenTSDB or HBase gurus. We also actually are using Redis very heavily now, where we actually kind of cache an immediate view of the of the whole network, so we can really quickly see at any time what the current state is. Let's get the next slide.
And this is our wrap up of the big takeaways, and what we learned from the last 5 years is that you should always stick to your core competencies. If your team's core competency is Erlang, don't select the Python based project as a core piece of your infrastructure and expect to be able to contribute to that meaningfully, or vice versa, or whatever the case is. Also, never assume something will be easy. It will become the most difficult thing if you assume that, as we learned in the case of reads. Also, even though we cited a lot of things that we encountered while running OpenTSDB that are less than ideal, OpenTSDB is a phenomenal piece of software that helped us launch a project, and I have nothing but the greatest respect for that entire project and its maintainers and contributors. We were just really high intensity users that didn't have a high enough level of Java knowledge to support support what we really needed to do, which was our own branch and custom modifications. We, at our peak, we were pushing over 250,000 writes a second and over 75,000 queries per second, which is not too bad. And the other big thing is that interacting with data on a terabyte scale, which will soon for us become the petabyte scale, is fundamentally different than interacting with any data that you have before. So thank you very much. There's our contact information. And also, if you want to listen to an in-depth discussion on our current metric system, you can check out a Packet Pushers podcast here that's linked. So thank you, everyone.